Okay, so I wanted to talk about the research paper. Obviously, with the current conditions, we're not going to be able to collect these data ourselves. So I'm going to give you some data from a previous class so that you can analyze those data and have the experience of writing a journal article style research paper, data analysis, but just unfortunately lacking the methods part where you'd go out and actually collect the data for yourselves. So the research that we're going to be doing is thinking about the leaves that evergreen trees have. Specifically, those leaves we refer to as needles. So you think about like pine needles or spruce needles. So these are these needle-shaped leaves that are found in evergreen trees. And these are leaves that they keep year-round. Now, one of the big benefits of having those needle-shaped leaves, right, because if you think about what leaves normally do, they do photosynthesis. But, having these little tiny skinny leaves doesn't seem great for photosynthesis. However, it does have the benefit of not losing nearly as much water. And so during the cold winter months, when there's not a lot of water around, when the air is relatively dry, when precipitation tends to be solid, these needle-shaped leaves have a small amount of surface area, and so they tend to have less evaporation taking place. And so these trees are able to keep their leaves year-round, but they have this trade-off of having to have needle-shaped leaves to do it, to avoid losing too much water. What we're going to be thinking about in this research is the effects that other trees of the same species might have on the length of the needles of these trees. So you can see in the picture in the top right, this is where the data were collected. Have a group of Norway spruce trees, and these trees are often relatively close to each other. And so what we're going to think about is how does that needle length vary depending on which tree we're looking at and how close another tree of the same species is to it. Now, I've divided this thinking then into two hypotheses. First hypothesis says, well, the trees that are closer together might compete with each other, right? So if you have another tree of the same species right beside you, well, that other tree is going to be trying to use, nutrients in the soil, water, the sunlight that's available. It's a possibility that one tree might shade another tree. And so competition for those resources might result in less resources being available, and so trees that are closer together might compete, resulting in shorter needles. The other possibility then is that when trees get closer together, that they could cooperate. For example, one way I could see cooperation happening is that when it's windy, right? Wind is something that tends to cause a lot of evaporation, but if there are other trees around to serve as sort of a windbreak, well, close trees then might decrease the amount of evaporation, might mean there's more water availability, might mean longer needles. We could also imagine that there could be below ground cooperation taking place. So things like the mycorrhizal fungi, this fungus that lives underground and helps trees capture nutrients and water from the soil, that trees that are in a stand close together might have more of those fungi all working together. You might have, again, an increase in resources and an increase in needle length. So for the study then, what was done was a group of trees had measurements taken of lengths of the needles. And so you're going to get a data file that has a whole bunch of measurements per tree of the length of the needles, and then a measurement to the closest tree of the same species. So how far away trees are, whether they're really close, really far, and then how long the needles are. And the measurements will be provided for you because unfortunately we don't get to collect our own data because we're not on campus this time. But you have the data and still be able to go through all of that process. Now, I'm going to have you write this paper then in the style of a peer-reviewed journal article. So the same sort of thing that you might read in a scientific journal is how I want you to write this. And so we're going to talk about what that's going to look like. The general parts of any peer-reviewed publication, scientific publication, is going to be an abstract, an introduction, a methods, results, discussion, and literature cited. So we're going to talk about what goes in each of these parts. And we're going to focus here on those middle four, the introduction, methods, results, and discussion. And those four are arranged in sort of what you think of as like an hourglass shape. Remember back when there used to be hourglasses in board games? Back before we replaced them with electronic timers that require batteries? Back when we had hourglasses that just did the same job but required no batteries or no extra input and lasted forever. And then we decided to switch to electronics so that every time you go to play a board game, you have to look for batteries because the batteries are dead. Wait, what were we talking about? Oh, right, hourglass shape. Wide at the beginning, narrow down in the middle, and then widen out at the end. That is the pattern of a scientific paper. So we're going to start out with the kind of broad, bigger picture with the introduction. So in your introduction, you want to start out with kind of the big picture, the ecological background. So in this case, that ecological background, you're going to be thinking about things like competition and cooperation, right? Those sort of big picture ecological interactions. That's what we're studying here, and so you want to start by describing those and what effects they might have on organisms. You can then move into the more specific background of the specific tree and the needles. So some tree background might include things like where this species is found, what kind of conditions it likes, and then what is the benefit of having needle-shaped leaves. And all of that should then lead directly into your hypotheses, where you explain what you think you might see with this research. It includes some rationale. So the hypotheses should be in their own paragraph, explaining the idea, what you expect to see, and then also kind of that rationale behind what you expect to see. All right, after introduction would come the methods section. Now, because you're not actually collecting the data, I'm not going to have you include a methods section. I'm going to send you an email with all the stuff you need. I'll include an example of the methods just so you have a pretty good idea of what happened when the data were collected, but you don't need to include a methods section because you're not actually carrying out the collecting of the data. The next section then, still in the narrow part of the paper, is the results section. And in the results, you are going to say what you found. So this is where you basically present the numbers. The results section is divided up into different parts. Results section needs to have a part of that's text. So here's an example of what some text might look like from a results section. These are just made up stuff, but you need to include actual numbers. I like to have things like averages and maxima and minima, ranges, just to get your reader kind of oriented to the data, right? You want your reader to know, is 20 millimeters a long needle or a short needle, right, or an average needle. And the text results kind of get them oriented. How many measurements were taken? What sort of range we expect to find on those? What sort of averages? What, in this case, what was the longest total needle? What needle measurement was the greatest? What was the longest average needle measurement? Those sorts of things. All right, you also need to have table results. Now, table results are never presented as raw data. So you're not going to have a data table that includes all the hundreds of measurements of needles that were taken. But you want a summary table. So here's an example that I just pulled from a study I was looking at about owls. And you can see in this table, you've got rows and columns of information. And so this is where you can indicate what sort of values you found in summary. So this is a good place for averages, for ranges. So in this case, you might have each tree, and then its average needle length, its minimum needle length, its maximum needle length, maybe standard deviation, and then the distance to the nearest tree. Right? It could all go in a summary data table. Yeah, you need to have at least one. You can have more than one, but you have to have at least one. Notice that there is a table label above the table, so table 1, and then a description of what's in the table. So every table needs to be labeled like this so that you can then refer to it in the text and say things like, see table 1. All right, the last part of the results then, you need to have graphs, so some sort of visual representation of the data. So again, here's an example of some owl migration data. I'm going to record another video where I talk about the data analysis and how to record the data and make graphs. But you need to have for this paper, at least one graph. You can have more if you think you need it, but you need to have at least one, which provides a way for the reader to see what things look like, to see what kind of pattern there might be in the data, and whether the hypothesis is supported or not. All right, after the results, you get to the discussion. In the discussion, you're going to start out by indicating whether your hypotheses were supported or not, right? So you're going to start out by saying the data supported that this. Then it's a good idea to compare your results to some other study with a similar sort of question. In this example, remember that you are studying these ecological interactions of competition and cooperation. So the study that you look at could be in a completely different organism, right? It could be the competition between, I don't know, mongoose as they hunt for rats, right? It doesn't have to do anything about trees. We just happen to be using trees as our study organism, but our question really about those ecological interactions. The rest of your discussion then is where you can really widen things out, kind of that big picture. Why does this matter? How can we apply this? How does this fit into general ecological theory? Right? You need to expand this out to the bigger picture explanations, to extrapolate out, to speculate about why this matters, and apply it if possible. I mean, you don't have to always apply things. I will just give you a hint. An application in this case might have something to do with the fact that Christmas tree farms are trying to grow a bunch of individuals of the same species relatively close together, and so you might be able to do something with how would you apply your results to how to space out Christmas trees, for example. All right, you'll also then, when you've written these other parts, you will then write the abstract. I recommend writing the abstract last, because the abstract is basically a summary of the rest of the paper. So the abstract will have, a sentence or two of background, a sentence or two of results and discussion, where you're kind of explaining what the overall story is. So you're kind of summarizing everything else and putting it into that abstract. Be specific in the abstract, so you can include things like the values that were obtained or the slope of a best fit line on a graph. You want to include actual numbers there. You also need to have literature cited, so especially in the introduction and the discussion, you'll be citing other studies. In the email I'll send out, it has instructions about how to do that, but just make sure that every time that you use another resource that you're citing that source and then including an entry in the literature cited section to indicate where that information came from. So the way that we'll do this is there's going to be a first draft. Hopefully that first draft will be relatively complete. We'll have all the parts. Will be a good first attempt. And then you'll get feedback and suggestions from me, but then also especially from your other classmates, where you'll provide that peer feedback just like happens in actual scientific publishing. And then you'll make changes and submit a final draft. In the email that I send out, it's going to have a lot of useful information. There's also going to be an example paper there, so that you can kind of base the format on that similarity to that example paper that's totally made up. You shouldn't cite it. It's totally made up. But it will provide you an idea of that format. Let me just also remind you that this paper needs to be written completely independently. So you can't work with anybody else on it. If you have questions, feel free to ask me. I'll be happy to help you. But do not work with any other members of the class. The Dropbox where we'll be turning it in will be a turn it in Dropbox. You need to put everything into your own words, and you need to make sure that you're doing your own work. If there's any evidence of academic misconduct, you'll get a 0 on the paper. So make sure you're doing your own work and ask questions of me when you need help. I'll be happy to help. We'll probably do the due date for this first draft probably about 2 weeks. I'll include that in the email when I send it out. Give you some time to work on it and ask questions. And find out anything you need to know from me to make your paper a really good first draft. So let me know what questions you have. I'm also going to send out an email with directions, and then I'm also going to post another video about the data analysis of the paper to help with that. So let me know what questions you might have, and hopefully this goes relatively smoothly, but don't hesitate to ask questions if it doesn't.